The video you are about to see is presented by Dr. Jacob Tao, founder of Galil Motion Control. In this 12-minute program, Dr. Tao will demonstrate Galil's easy-to-use technology with an emphasis on PID tuning and motion profile capabilities. In the last 10 years, Dr. Tao has authored numerous books and technical papers on motion control, and his seminars have attracted over 10,000 engineers. Galil has deployed over 250,000 motion controllers worldwide.
Hi, I'm Jacob Tao, and I would like to give you a demonstration of tuning a digital system and generating motion using the Galil WSDK program. First, the components we have. We have a host computer here. We have a motor with an encoder. We have a power amplifier to drive the motor. And we have a motion controller. The controller is the intelligent part in the system. This is the brain of the system. This particular controller happened to be the DMC 1425, which is a 2-axis controller. Galil has a wide family of controllers that could control anywhere from 1 axis up to 8 axis controllers, and they communicate with the host in several ways. Some of them plug into the bus, such as PCI and ISA and VME. Some communicate serially with RS-232, Ethernet, or USB. Before we start, we need to communicate between the host and the controller. And to do that, we use the Galil language. Galil has developed a language that's very easy to use and friendly English-like, as a matter of fact. If the host needs to know the position of the X motor, it would send the command TPX, as we see it here. And TPX stands for Tell Position X. In response, the controller sends the number -12, implying this is the position counts. In a similar way, if we'd like to interrogate the error, the command would be TEX. TEX stands for Tell Error X, and the response is -12. The language includes more than 200 such commands that address different conditions for the operation of the motor. We need to get the system tuned, because a tuned system is first stable, and secondly, it's responsive. We want the motor to follow our commands very rapidly and tolerate disturbances in the system, and that's possible by the stability. The mechanism for tuning the system is through a digital filter that's programmed in the controller, and that filter is known as a PID filter. The PID filter has 3 parts, P, I, and D. P stands for proportional, and that part of the filter would assure that the system is responsive and moves fast. D, the derivative, assures stability. And I, the integral, makes sure the system is accurate. Between the 3 of them, we achieve everything we need. Now that we've seen the role of the PID, how do we select the PID? We at Galil have looked at this problem for a long time. As a matter of fact, about 20 years ago, when we were the first company to introduce a digital PID filter in a motion controller, the first question we addressed is how to make it easy for users to tune the system, and we came up with the method of automatic tuning. And over the last 20 years, we've been improving on that. So the WSDK that you see now is the most recent revision in that process. And what I would like to do is show how such automatic tuning could take place. We'll go to the WSDK and click on the tuning method. And in here, under the tuning method, notice that there would be several methods. There is the auto crossover, there is a crossover frequency, there is a general tuning, the point-to-point, curve follower, and manual. First, why do we need so many tuning methods? And the answer is that there are different applications, and different applications require different tuning methods. To date, Galil has sold over 250,000 controllers worldwide, and those run different applications, and different applications are tuned differently. For example, if you're designing a tester that needs to move point-to-point, then the best tuning method would be the point-to-point. If you're designing a cutting machine with a plasma cutter, then the best tuning method would be the curve follower, because it has to follow a certain curve. As for general tuning, you do general tuning. So the different methods fit different situations. And what I would like to do is to demonstrate the quickest and simplest method, that's the auto crossover. To do that, all I have to do is click on the start button. I don't need to specify any parameters. I don't need to know the inertia of the load. I don't need to know the encoder resolution, the amplifier gain. Just start the process and notice that the controller would drive the motor, identify all the parameters, and then on its own it would experiment with different bandwidth until it stops at a certain frequency that it thinks that the system is working best. And once it's done, it displays a step response. Notice what we're seeing here is a step response, and it looks pretty good. We exercise the motor, we send it back and forth between 0 and 400 counts, and notice the step response is very good, very smooth, and very stable. And this happens with a crossover frequency of 534 radian per second. Now that we got the system tuned, we'd like to command some motion. And the commands are done by instructions. Let me show you an example. If I send the command PR 4000, in the Galil language, PR stands for position relative, indicating a relative move. The number 4000 is the encoder counts we need to move, which in this case corresponds to 1 revolution. So PR 4000 is the same as saying turn the motor 1 revolution forward. Now, in a similar way, we could program the speed, and the speed command is SP. If I set the speed to a low value of 2000 counts per second, that would be the speed. In a similar way, I could program acceleration, such as AC 200,000 counts per second square. I could also independently program the deceleration at 200,000. Now, if I issue the BGX mode, it would start the motion. Notice the minute I press the return, the motor would move 1 revolution, and it moves fairly slowly. That's because the speed is low. I could repeat it with higher speed. If I set the speed to 40,000 and repeat the motion again, the motion would be much faster. The motion I just demonstrated moved the motor from one point to the other, and it's called point-to-point motion.